Let's perform a similar analysis with this quadratic function. We want to graph it, we want to find its intercepts, we want to talk about the domain and range of this quadratic function, and we want to talk about the intervals of x across which the function is increasing or decreasing. The way we start in our analysis is we first find the vertex. And remember, the vertex of the parabola is found by first finding the x value, which is negative b over 2a, then taking that value, evaluating the function in order to get the y value of the vertex. So in this particular instance, the x value of the vertex is going to be negative b, so that's negative 6, over 2a, that's 2 times negative 3, which gives us negative 6 over negative 6, which is 1. So the x value of the vertex point's x value is 1, and now let's evaluate f at 1. So that's going to be negative 3 times the square of 1, plus 6 times 1, plus 2. The square of 1 is 1. Negative 3 times 1 would be negative 3 plus 6 plus 2. 6 and 2 is 8. 8 added to negative 3 gives us 5. So the vertex value here, the vertex value is 1, 5. So here is the vertex of our parabola. And in this case, does our parabola open up or open down? Well, the coefficient of the squared term is negative. That tells us our parabola will be opening downward. Well, let's see if we can find some other points that we can graph. Because remember, this parabola, like every parabola that is the graph of a quadratic function, it's symmetric around a vertical line. That vertical line is no longer the y-axis, but it is the vertical line x equals 1. So we call that again the axis of symmetry. So in this case, the axis of symmetry is the vertical line x equals 1. Well, let's find some intercepts if we can. The y-intercept is always the easier intercept to find, because we find the y-intercept by simply letting x be 0. And if I let x be 0, those terms disappear into 0, leaving me just a function value of 2. So the y-intercept is the point 0, 2. So when x is 0, y is 2. There's my y-intercept. And now I can get a symmetric point. I went 1 unit to the left on the x to find the function value here of 2. So if I go 1 unit to the right, the function value also has to be 2 for the symmetry that we have here. So when x is 2, the y value is also 2. Just like when the x was 0, the y value was 2. Now, we could find the x-intercepts. To do that, remember, to find the x-intercepts, you let the function value, you let the y value be 0, and you solve the resulting quadratic equation. Well, in this instance, when I solve that quadratic equation, it ends up being irrational values. We have to use the quadratic formula. It doesn't come out to nice whole numbers. It doesn't come out to nice rational numbers. It's irrational values. And if we approximate the intercepts, we would find that we have our two x-intercepts are 2 3/10 0 and negative 3/10 0. So they're not nice, pretty x-intercepts, but I found those by using the quadratic formula to solve that quadratic equation. So that would be 2.30, which is roughly here, and negative 0.30, which is roughly there. And those points are sufficient then for us to be able to draw the parabola, draw the graph of that parabola. We which again happens to be a parabola that's opening downward. The negative coefficient for the squared term indicated that to us and produced that graph for us. Well, let's talk about the domain and range then of this function. Again, the domain is all real numbers. There's no restriction on the domain of this quadratic function. The range, well, the graph, the y value gets all the way up here to 5, doesn't it? And then it contains all of the values, all the y values, all the way down to negative infinity. So the range would be from negative infinity up to and including 5. And so in interval notation, we would express it this way, as the range of that quadratic function. And then across what intervals of x is the function increasing or decreasing? Well, the function is, as we move from the left, as we move from negative infinity for x, isn't the function coming up until it reaches its high point here? Its maximum point there? In fact, that's the case. At the vertex, the function always has either its maximum value if it opens down, or has its minimum value if the parabola opens up. And that'll be very important in some things we're going to look at later. But the interval across which the function is increasing is as the x's go from negative infinity to 1, and then at that point it turns. So from negative infinity to 1, the function's value is increasing, and from x values of 1 out to positive infinity, the function is decreasing. And we have analyzed that quadratic function in terms of its graph and in terms of information about the function in this process.